welcome to the 35th lecture in our particle characterization course. In the last lecture, we began a discussion of filtration technology. Filtration is a discipline that involves many aspects of particle characteristics, in particular size and shape, and we looked at several examples of different kinds of filters and the filtration efficiency in terms of its relationship to particle properties, in particular size and shape. Today we are going to continue the discussion of particle control technologies. A good example of that is a clean room. A clean room is essentially an isolated environment in which the level of contaminants in the air is controlled in an active manner. So, these contaminants could be particulate in nature or they could be chemical in nature as well. And essentially what we try to do is within this enclosure, which is well sealed so that there is no leakage of outside air into this room, and the only passage for the air to enter the room is directed through filters. As we were talking about in the last class, there are HEPA and ULPA filters that are used to treat the incoming air just before it enters the clean room enclosure, and the design ensures that's the only way outside air can enter the clean room. So, in principle you can control the cleanliness of this clean room facility by ensuring that air only enters through one passage and that passage is completely filtered to remove unwanted particles of various size ranges. And you can also use chemical filters. For example, if you use activated charcoal as a filter, it will remove all organic materials. If you use a bicarbonate filter, it will remove the inorganic materials. But in particular, we are going to focus on particulate filtration. Now, a clean room, if you want to sketch it, it essentially looks like a box. Now, this is the ceiling, and it essentially has a false floor. It's called a raised floor. The ceiling also has a duct in which the filters are placed. So, in this area you will have coverage through filters, and the incoming air will essentially be forced through these filters and then made to exit into the clean room. So, this is where your HEPA filters and ULPA filters will be located. Now, the most popular design for a clean room is what is known as a vertical laminar flow clean room. In a vertical laminar flow clean room, it's also known as a VLF clean room, the air enters the room at the top through filters that are located on the ceiling. It is then directed into the room in a unidirectional manner. The flow, airflow is controlled in such a way that all the velocity is vertically down. Now, the problem with that approach is the airflow will keep coming down, but then when it meets the floor, what is going to happen? Essentially you are going to get stagnation flow. So, you are going to start getting some recirculation, convection rolls and all that, which is not good, because in a clean room what you want to avoid is such phenomena as natural convective flows, convection rolls and so on, because they extend the residence time of particles inside the clean room, and the longer the residence time of particles, the greater the probability that they will deposit on critical surfaces and cause yield losses and reliability failures and so on. So, in order to avoid this, what you do is essentially have a false floor or a raised floor which has holes in it. So this air is drawn through these holes and then it's exhausted out of this false flow. So all the air is essentially made to leave in this fashion. So again, you do have stagnation flow, but now it's below the critical manufacturing location, because all the manufacturing operations are only taking place in this area. So within this area, the flow remains essentially vertical and laminar. So this is the ideal configuration. In a clean room, you don't want turbulence to happen. You want all the airflow to be at high velocity and directed in such a way that it takes particles that are located inside the clean room and as quickly as possible purges them out of the clean room. So this is kind of the overall setup that you want to have. Now, what are some of the challenges in operating such a clean room? This air that you are venting out, if you can continuously keep exhausting it to the atmosphere, that will provide the best cleanliness, because you keep bringing in clean air, it gets dirty inside the room and then you vent it out, right? The problem is the energy consumption, airflow usage is very, very high. So to operate a clean room in this fashion may provide the best controls on the levels of particles, but it's also the most expensive way to operate a clean room. So instead, what you do is you take some fraction of this outflow and recycle it. So you build in a continuous recycle loop which minimizes the total air handling that your filter systems have to do. So it basically reduces your intake air. If this is your intake and this is your recirc, the total airflow into the clean room is the intake air, or it's also known as the makeup air, plus the recirculated air. So clearly the recycling strategy has certain benefits in terms of cost controls, but from a particle control viewpoint, it's obviously not as good unless the external environment is much dirtier than the interior environment. For example, if you have a clean room operating in the middle of an urban area where there's a lot of automobile exhausts and so on, it's possible that the outside air is much dirtier than the inside air where the process is going on. In that case, actually this will give you both benefits. It will give you a lower cost and it will also give you a cleaner facility, because you are minimizing the amount of air that you are taking in from the outside. So this ratio of recirculation volume to makeup volume or intake volume of air is a very critical parameter, and it needs to be optimized for every clean room application you have. So in order to do that, what do you do first? You have to develop a model for the clean room, right? So you have to do CFD modeling to obtain a predictive description of how the flow field in this environment will behave. If you look at this, it's a classical fluid dynamic problem. You have essentially a fixed control volume, which is a clean room that material is entering and leaving. And it's essentially a two-phase flow. You have the gas phase, in this case air, and you have entrained particles in it. Now depending on the size of the particle, some of them you may treat as single phase, but as the size of the particle becomes larger, you have to treat it as a multi-phase problem. So it's kind of a combined single phase, multi-phase problem. And there are classical methods of solving this problem. You can essentially write down the conservation equations. For example, you can write the total mass conservation, assuming density is constant. You can write it as del u by del x plus del v by del y plus del w by del z equal to 0. These are the velocity components in the different x, y, and z directions. So you can actually do a very rigorous 3D model of this clean room. And then you would write the momentum conservation equation as del u by del t plus u del u by del x plus v del u by del y plus w del u by del z equals 1 over rho del p by del x plus nu times del squared u by del x squared plus del squared u by plus del squared u by del z squared. So, classic equations, momentum conservation equations, Navier-Stokes equations can be written, and also if this is a non-isothermal clean room where there are significant temperature differences, you also have to write the accompanying energy conservation equation and then solve everything simultaneously. You have to apply the appropriate initial conditions and boundary conditions. For example, the initial condition for such a facility may be that the starting point of a clean room is where essentially there is no source of particles inside the clean room, and all you have is air entering and air leaving. So, you can look at the time 0 point as a steady state where essentially there is no contamination source in the clean room. The boundary conditions you will have to impose for the various situations. For example, along the walls you can say no slip boundary condition, which is a Dirichlet type of boundary condition, but near the flow paths, the intake path as well as the outflow path, you may want to impose a Newman type of boundary condition which says that the gradient is 0, del v by del x or del v by del y equal to 0. So, by applying the appropriate initial and boundary conditions, you can essentially set up the model, solve it numerically using finite difference approximation, and you can actually get a very precise description of how the flow field will look like, the velocity distribution, and you can also predict how the particle concentration distribution will look like inside the clean room. And in fact, we have done that exercise in our lab. We have developed a model for the clean room in the Department of Electrical Engineering, and we have actually matched our predictions to particle counts that we take with an airborne particle counter, and the two match pretty well. So, it is certainly possible to deal with this problem in a mathematically rigorous fashion, but the limitation to that is that the model that you develop in this fashion obviously is a very simple model in the sense that it does not account for the various complexities that can enter. Because I mean the assumption here is it's an empty room, but that's not true. I mean any clean room in which a manufacturing process is running, it's going to have all kinds of things in it, right? It's going to have workstations on which you're going to have some pots that are sitting there. It's going to have people, again, people may be standing, walking, moving around. It may have various pot storage locations. People may be wearing garments, gloves, but most importantly, this person is going to be doing something. So, there may be two parts that are getting assembled together. So, when you assemble anything, you generate particles, right? So, all of these subtleties really cannot be captured in a very rigorous model. Well, you can, but then the complexity of the model will become so high that the CFD code may take forever to run a single simulation. So, it becomes somewhat useless. So, instead what you can choose to do is develop a simpler model for a clean room. For example, you can assume that the clean room is essentially well mixed, so that particle concentrations everywhere inside the clean room are uniform. Now, that might actually appear to be in conflict with the vertical laminar flow type of a model, because I mean by definition this says that the contamination level, particle levels are going to be lowest near the filters, and they are going to keep increasing as the air flows down towards the floor. So, it's a questionable assumption, but it will make the model easier to deal with. The other assumption you can make is all the flow rates are essentially in steady state, constant flow rates. You can also assume that concentrations are not varying with time. So, essentially you can simulate a quasi-steady approximation to the operation of a clean room. Now, when you do that, the picture is going to look like this. Again, you have the clean room and you have particles coming in. Now, there is usually a pre-filter, as we discussed in the last class, the pre-filter is likely to be a fibrous filter, whereas the HEPA and ALPA filters here are likely to be membrane filters. And then you have the bottom. So the flow comes in like this, goes to the filter bed, enters the clean room, and gets exhausted outside. I mean, this is basically the flow path that the airstream will follow. So all entrained particles will also follow the same pattern. Now let's say that some part of this is now being recycled and going over there. So how do you develop a simple steady state model for this? What you're interested in is predicting the steady state particle concentration inside the clean room. So let's say that what emerges through these filters is a uniform concentration of particles inside the clean room. Let's call that CC. Okay? So this is the uniform steady state concentration of particles inside the clean room. Now in the ambient air you are going to have some concentration of particles. Let's call that some Ca. Okay? Now the pre-filter is going to remove some percentage of that, and so you will have a, let's call that CPF, which is the concentration of particles as it comes out of the pre-filter, and then once it goes through the final filter in the clean room, it emerges with a concentration Cc. Okay? Cc is now the concentration of particles that is uniformly distributed in the clean room, which means that in the outlet stream also the particle concentration is going to be Cc, right? It's like a well-stirred reactor. So the exit concentration will be the same as the concentration of particles inside. You know, if you want to look at this clean room as a reactor, that's probably a good analogy. Now the other concentration that we have to be aware of, I mean, what are we missing here? Is this a full picture, or is there a term that we are missing? Just think about particles. What is the basic assumption here? The basic assumption is all the particles are only coming from outside, but we know that's not true because particles are also getting generated inside the clean room. So you need a source term. Let's call that some Cs. So there is a source of particles inside the clean room which is contributing to the total level of particles. If that is the case, then clearly this is not the concentration here, right? It should be Cc plus Cs. So that is the concentration of particles in the outlet stream from this clean room. Any other sources or sinks for particles that we should be aware of? Well, there will always be losses due to sinks at the walls, for example. But let's say that for the time being we ignore all that. Let's say that all particles are entering, being generated, and then being exhausted. Now the other parameter that we need to know in order to do a mass balance on this is flow rates, right? So let's say that there is some flow rate Qa that is entering the pre-filter, and the flow rate doesn't have to change as it goes through the pre-filter, and the flow rate into the clean room is also Qa. So the flow rate we are assuming is not inhibited by the presence of the filter, which, you know, again may not be a good assumption. As we talked about in the last lecture, especially with the final membrane filters, pressure drop can keep building, so there can be substantial losses of flow velocity with time, but in a quasi steady state model you can assume that it's a reasonably steady process. So then the outflow at this point is also going to be Qa since it's operating under steady state conditions, but part of that is now going to be recycled and part of that is going to be exhausted. Okay? So here again, what does that mean? If Qa is the flow rate coming in here and you are now adding Qr, then this becomes some Qi, let's call it, entering the clean room, Qi, which is equal to Qa plus QR. So this is now actually QI, right, because it's basically a loop in which you are taking flow and redirecting it to enter the clean room back in a recycle mode. So here again this is going to change to a QI, and again you are going to keep taking some fraction of it, and so under steady state conditions the total flow rate that enters the clean room is going to be whatever you are recycling plus whatever is entering as makeup air. So this is the overall flow dynamics for the clean room. Now the question that we have is, if you look at this parameter Cc, let us assume that Cs is constant, right, it is not changing. So what you want to actually minimize is Cc plus Cs, Cc plus Cs to be minimized, or because Cs is constant we will say that Cc is to be minimized. Now what is the what parameter do you have control over? Let us assume that the efficiencies of the filters are fixed, so you really cannot change that, and let us say that the outside ambient concentration is fixed, the flow rate through the filter from the ambient is fixed, and let us say that so you do not have any control over those parameters, and let us say that the filter efficiency of the HEPA and alpha filters is also fixed. The parameter that you have control over is essentially QR over QI. What percent of the material is being recycled back into the clean room? So Cc will be a function of this, right, and the thing is that if Cs is much greater than Ca, in other words if the source inside the clean room is much stronger than the source outside the clean room, logically you would think that the less the recycle the cleaner will be the clean room, whereas if it is the other way around, if Ca is much greater than Cs you would expect that the greater the recycle the cleaner will be the clean room. So clearly these two are related. For a fixed Ca value this parameter really controls the cleanliness of the clean room, but on the other hand it is a constrained minimization problem, right. You cannot say for example if the source inside the clean room is much greater than the source outside, logically you would say make it 98% recycle and only 2% makeup. That is not practical because you really cannot handle that volume of air with a pump and get it recycled, especially in a large clean room. So there is a cost associated with the recycle. So the cost of recycling also is a function of the same parameter QR over QI. So this can be formulated as a classical optimization problem where you try to minimize Cc subject to a constraint on the cost of the recycling. You set either a maximum allowed or something that is maybe based upon a relationship between quality and cost, or it may be something based on reliability and so on, but it is a constrained optimization problem. Now if you do a simple mass balance on this, you can establish this relationship, right. Using this loop you can actually calculate Cc as a function of all the other parameters in this model. So I encourage you to do that. I think it is a good exercise to set up the relationship between Cc and QR, and then try to do this as a minimization algorithm. Take dCc over dQr equated to 0 and understand the conditions or the value of QR which gives you a minimum in Cc, and similarly we can establish, the cost is essentially going to be a linear function of the flow rate, right. So the only constraint that you can place is the maximum cost, because this is not a non-monotonic behavior, it is a monotonic behavior. The more recycling you do the more it is going to cost you to recycle, and it's fairly linear. I mean, if you recycle twice the volume, you'll pay twice the amount. So the first part I think is something that you can do separately as a minimization exercise, and it'll give you a value for QR, which gives you a minimum in CC, and then if you're given this number about cost of recycling, and you're given that something is the maximum that you can afford to pay, then you can compare your optimum value of the recycling rate to the maximum value that's allowed from a cost viewpoint and ensure that you're below that level. If you're not, then you have to operate under suboptimal conditions. You have to reduce the amount of recycling and perhaps live with a higher CC value, but with a correspondingly lower cost. So that's a kind of exercise that clean room engineers go through. No manufacturer has infinite resources at their disposal, so they are constantly doing this juggling to see what is achievable versus what is desirable given the process economics and so on. Now this also indicates that as I've said before, if you cannot measure something, you cannot control it. I mean the assumption here is we know what these values are, but how do you quantify CS, how do you quantify CC? So you need good equipment and instrumentation to be able to measure particles in the clean room air as well as on clean room surfaces. You might want to know how many particles are there on a workstation inside the clean room. How do you evaluate that? Because until and unless you know that, you really cannot estimate these concentration values. So methods of measuring particle concentrations become important when you are doing this modeling of a clean room and trying to optimize its operation from a cost viewpoint. Now the other thing also you have to keep in mind is when you solve the Navier-Stokes equations or even the simplified quasi-steady model, what you're really getting is a picture of how airflow is developing over the clean room, and if you solve the two-phase model, you can also get a description of particle velocities inside the clean room. You'll get a distribution of particle velocities, but from that you have to extract particle deposition rates. Now as we have discussed in earlier lectures, the rate of deposition of particles on surfaces is a distinct parameter from the velocity with which particles are transported inside the clean room. So if you look at, for example, this clean room, what you really care about is, suppose you have a silicon wafer sitting here, how many particles are going to deposit per unit area for some period of time. Ultimately that's what you care about, right? You're not going to ship the clean room to the customer. What you're going to ship to the customer is the wafer that you make in the clean room, and if you can make a clean wafer inside a very dirty clean room, then you don't care how clean the clean room is. But unfortunately that's not how it works. I mean basically if your clean room is clean, you get a clean wafer. If your clean room is dirty, you get a dirty wafer. So there is a correlation between the two, but ultimately what you care about is keeping your product clean. So what we need to think about is again the Nusselt number for mass transfer. So in this case the Nusselt number for mass transfer for particles becomes the most critical dimensionless parameter that we need to track inside the clean room. Now this number is a function essentially of the Reynolds number and the Schmidt number, right, as we have seen before, and again normally this would go approximately as Reynolds number to the power half, Schmidt number to the power 1/3, where of course the Schmidt number is the ratio of nu by d, momentum diffusivity to particle diffusivity. But this is under what conditions? The zero conditions, right, assuming that there are no phoretic phenomena. But inside a clean room actually the phoretic forces are very strong, because for one thing electrostatic forces are pretty high in magnitude inside a clean room. The reason for that is that the clean room is so clean that static charges develop very easily. Low humidity conditions are especially conducive to development of charge. I don't know if you have noticed it, but the drier the atmosphere, the more that static charge develops. You can almost feel it, right? and clean rooms are operated with tight controls on temperature and humidity. Humidity is typically kept to 55 to 60% or less. So under such conditions, static charges develop very quickly inside a clean room. So if you look at forces that deliver particles to surfaces inside a clean room, electrostatic forces are probably number one. I mean, in addition to the normal mechanisms of convection and diffusion and so on, which are accounted for in the Nusselt number, but you remember that we have to then multiply this with an F correction, right. So this the basic, this only involves convective and Brownian deposition of particles. In order to account for all the other phoretic phenomena, you have to apply a correction factor. So this F correction will have F due to electrostatic forces, and it will also have a correction factor due to thermophoritic forces, because again in a clean room the wafers, the product that's being worked on will tend to be at a slightly elevated temperature compared to the facility away from the product, just because there are people nearby, there are tools doing operations, all of that in addition to generating mass also generates heat. So the product that you are working on inside a clean room is always going to be hotter than the environment surrounding it, so there will be a temperature gradient that develops, and as soon as there is a temperature gradient you have thermophoresis as a force to deal with. So you have to add in a correction factor for thermophoresis. Now what other forces do you have to worry about? If you are handling magnetic particles, for example if you are doing disk drive manufacturing, the disk itself has magnetic media, so it's very likely that many of the particles that become airborne are also magnetic in nature, in which case you may have to have a correction factor for magnetic forces. The other type of flow that we have talked about earlier is gravitational, right. Unlikely in a clean room, it's very unlikely that you have large enough particles that gravitational settling or sedimentation becomes an issue, because these filters are very very effective in removing such large particles. So F gravitation is considered negligible inside most operational clean rooms. The other effect that we have talked about is Stefan flow, which happens because of a convective flow that opposes diffusion, but that again is unlikely to be important because Stefan flow is only important for non-dilute systems where there are significant concentrations of particles in suspension, and if you don't have that then you don't have to worry about Stefan flow also. So the last two can be neglected, but electrostatic effects, thermophoritic effects and magnetic effects in some cases are important correction factors that you have to develop and apply as appropriate. Now how do you do that? You may remember that for each of them there is an associated Peclet number. So there is a Peclet number for electrostatic, Peclet number for thermophoresis and so on, and the correction factor itself is typically written as Peclet number divided by 1 minus exponential of minus Peclet number, where the Peclet number is defined as a characteristic velocity that is associated with the phoretic force. So this could be a electrostatic velocity, it could be a thermophoritic velocity, or it could be a magnetophoretic velocity, and it's multiplied by a characteristic dimension. So in this case the characteristic dimension would most likely be either the diameter of the wafer if it is a circular wafer, or it could be the length of the wafer, but some characteristic length of the deposition surface divided by a diffusivity value, which measures the importance of these mechanisms relative to diffusional mechanisms. So for each of these you calculate or you measure the corresponding velocities, develop the Peclet numbers, from the Peclet numbers you arrive at the correction factors, and then you apply that to the Nusselt number to get the actual So, this is the prevailing Nusselt number, which is the multiple of the convective plus Brownian portion of the Nusselt number times these correction factors. So, once you know the Nusselt numbers, you can calculate the associated rate of deposition by multiplying this by the reference quantity for deposition flux. Now, this exercise is important to do because the thing that we need to really work on inside a clean room is, in addition to controlling the particulate levels in the environment, the placement, orientation and time of exposure of product are the three most important variables. Placement, because if you place your wafer here, the rate of deposition may be very high, but maybe if you place it over here, it's very low. So, you have to do some mapping of airflows, particle levels in the clean room, identify regions that are relatively clean compared to regions that are dirty, and make sure that you perform your most critical processes and expose your most critical components only in the cleanest locations. So, location is important. Orientation is important because if you orient the surface horizontally in this example, the rate of deposition is going to be very high because stagnation flow can develop over the wafer, whereas if you locate it in a configuration where it's parallel to flow, then deposition due to impaction, for example, will be distinctly reduced. And the time of exposure is critical because rate of deposition is essentially a time dependent process. The longer you expose the surface, the more material will deposit on the surface. So, even in a very, very dirty clean room, if you have a way of providing what is known as mini environments, these are enclosures that fit around the product that you are making, then you can actually protect the product. For example, in this clean room, the entire clean room may be a class 1000, which, as you know, is pretty dirty, right? But around the product, you can actually design a mini environment which is a class 10. So, it's 100 times cleaner, and you make sure that you never take that product out of this mini environment. So, this could be like a cassette carrier, right? So, the wafers could be placed inside cassettes, and then cassettes could be loaded inside this mini environment, and you could just move the entire mini environment from stage to stage in the process. So, that way you do not really expose your product to a dirty environment for very long. You essentially keep it sealed in a sterile environment as long as possible. Just before you are ready to do something to it, for example, you want to take the wafer and put a pattern on it. So, just before you are ready to put the pattern, you remove the disc from the wafer, you remove the wafer from the cassette, put the pattern on it, and immediately put it back into the cassette and seal it again. So, by minimizing the time of exposure, you can also control the extent to which particles can deposit on the surface. The other thing that you should always be on the lookout for is emission rates. When you have equipment inside a clean room, associated with each equipment, there is a rate at which particles are getting emitted from that equipment. There is a measurement technique called particles per wafer per pass, which is a very useful technique to measure particles that are being generated from clean room equipment. So, essentially what you do is you take a clean wafer, and let us say that there is some tool on which you are loading in the wafer, doing something to it, and then taking it out, right. So, you measure the level of particles on this wafer before it enters the equipment, and then you cycle it back through this equipment 10 times or 100 times, and then you measure total particles on it after being cycled through this equipment or process, let us say 100 times. So, you take the difference between n final minus n initial and divide it by number of passes through the equipment, and that is called particle per wafer per path measurement. Now what this is telling you is how many particles are being added to the wafer simply by cycling it through the process equipment that it has to go through, and it gives us a way of monitoring how clean or how dirty this tool is. Now what you can have is, let us say that if you have this number being measured, you can have a spec on it. You can say that if it exceeds a certain number, I am going to shut down the tool, clean it completely, and then put it back online. So it gives you some endpoint control. The only downside of this type of measurement is it is somewhat after the fact. I mean, what you are really measuring, by the time you measure this on the wafer, you would have already processed many wafers through this, right. So you may have to sacrifice whatever that production lot is before you make the fixes. So it's better to have a real time monitor to look at how particles are getting emitted from the equipment. So what we normally do is, in addition to this particle per wafer per pass methodology, in addition we actually have particle counter tubes that are constantly measuring particle levels within this tool enclosure. So this is different from the particle measurement devices that we have for the clean room. Usually the particle counters that measure clean room air are located near the filters, to measure how clean the air is when it comes into the clean room. Here what we are talking about is locating these particle counters right where the process is being done, inside the process tool. For example, if I am putting down some patterns on this wafer inside this tool, you actually stick this particle counter as close to that operation as possible, so that you actually measure how many particles are being generated by the process of putting this pattern on the wafer. And of course this will also include contributions from the equipment itself. The equipment is different from the process. An equipment is just a piece of machinery. A process is what you do with that equipment, and they both have contributions to total particle levels inside the clean room, and you have to be able to measure them separately, and you have to be able to measure the clean room contamination levels separately. So this differentiation of sources is very important, because it allows us to do a Pareto type of analysis to identify the top contributors of particles in a clean room and then take steps to minimize them. The Pareto methodology is one that essentially enables us to rank sources of particles inside a process. So the way that works is, in a Pareto chart, you will take all possible sources of particles inside a clean room. So for example, the clean room facility itself is a source. That is the air that's coming through the filter itself, they are all sources. Clean room equipment is another source. The clean room process, what is being done inside the clean room, is a source. People are a source. The gloves, swabs, other consumables that are being used inside the clean room is a possible source. Chemicals that are used in the room are another source, and so on. I mean, you can actually critically analyze and identify possible sources of particles inside a clean room, and then you actually assess the magnitude of each. So you have to have a way of measuring the number. How many particles are contributed by the facility, how many are contributed by the equipment, and so on. If you can do that quantification, then you can actually develop a bar chart. So Pareto analysis simply says you draw these bar charts including all possible sources of particles in your process, and then identify the top hitters. For example, in this case we could say that even though these are all possible sources, these three contribute 80% of all particles in my process. So I am going to go after those. That is important because any organization has only limited resources, both in terms of manpower as well as financial. So you cannot clean up everything. Ideally you would like to get to 0 particles. It's not possible. So you want to make your investments where they will do the most good. There's no point in spending a lot of money to clean up your chemicals if they are very low in your list of priorities, right? Based on the magnitude of contribution of particles, they are very low compared to some of the others. So the Pareto type of analysis helps you to essentially get the most bang for your buck, so to speak. It enables you to make your investments where they will do the most good, where they will have the most dramatic effect. So here, for example, if I find that the clean room facility is the biggest contributor of particles, then my first approach should be to improve the filtration so that I can have finer filters maybe to clean up the air that's coming in, or I may want to look at the recycle ratio. Maybe I'm recycling too much, maybe I'm not recycling enough, so I need to look at that. The other thing I would do is look at the airflow patterns. Are they really flowing in that vertical laminar flow configuration that we wanted, or is something happening inside the room and I'm getting mixed flow, turbulence, recirculation, stagnation? So I would want to do some airflow modeling in this case. On the other hand, if I find that the equipment is contributing particles, then I would want to look at, is the equipment properly designed? Is it made of the right material? Does it have the right surface finish? Are some surfaces too rough and contributing particles by abrasion mechanisms? Or is it that there are some oils that are spewing out as aerosols and getting counted as particles? If I find that the process is a major contributor, I would want to look at, do I have too many mechanical assembly processes? Because when you try to, for example, screw a nut into a hole, you generate millions of particles. So maybe instead of using screws, I should be using tapes in order to assemble 2 components. Maybe much cleaner. Maybe you may reduce the particle generation by 10 times simply by going to an adhesive process rather than a mechanical assembly process. Or you may find that you're just doing the process the wrong way, in the wrong order. Maybe you're not putting the components together in the right sequence. So you can just change the sequence of the assembly and improve the particle levels. People, if you find that people are a major source, maybe they are not wearing the right garments. The primary thing that keeps people from contaminating a clean room is the clean room garment that they wear. So maybe we have to upgrade the level of the clean room garment that they are wearing. So associated with each of these sources, there is a list of corrective actions. But the point is, you cannot afford to implement all of these corrective actions across the board. Just too expensive, too disruptive. So this Pareto strategy enables you to home in on specific sources that are potentially high contributors of particles and other contaminants to your process, and enables you to come up with strategies to minimize those preferentially over all the other sources. Now ultimately what you want to do is link this to some product performance characteristics. And when we talk about product performance, particularly in high-tech manufacturing, the 2 important metrics are process yield and field reliability. These are absolutely important because process yield affects your profitability, field reliability affects customer satisfaction. And for any large volume manufacturer, those are the 2 most important mantras that they live by. If you have a high process yield and if you have high field reliability, then you are in business. If you don't, you are basically out of business. Okay? So in the next lecture, we will particularly focus in on these 2 indices, process yield and field reliability, and look at how particle characteristics in particular can affect these 2 critical parameters. Any questions on what we discussed today? Okay, see you in the next class then.